So for this video, we'll be examining the mechanics of a disk going down an incline. So when some disk or some object, in this case it's a disk, goes down an incline, it's going to have a torque, an inertia, and an angular acceleration. So some people, or most people, wonder if you have these two disks that go down at the same time, which one would get to the bottom of the incline first? Some people would say the heavier one would, others might say the lighter one would. But as we'll see, it actually doesn't depend upon mass. It only depends on the shape and the weight distribution of what's going down the incline. So what we know about torque is that an object's torque is equal to its inertia multiplied by its angular acceleration. Now, this really doesn't tell us much in terms of showing how one object will get to the bottom faster than the other. So what we can actually do is solve for the object's translational acceleration. In this case, that would be a normal A, which is equal to the radius of the object multiplied by the angular acceleration. I'm saying radius in this case. Really, it should be the point of contact of the object between its center and mass. But I'll just use r and radius to make things simpler. So when we look at this, we can translate torque into a force that isn't rotational. So we know that torque, much like our translational acceleration, is equal to radius times the force. And then since it's going down some slope, it will be sine of the angle of that slope. We know that force is mass times acceleration, so we can write this also as radius times mass times gravity, in this case acceleration, times the sine of this angle. So our main goal is to solve for this. So what we can do is have, we have r n g sine of theta is equal to I times A over R. Then we can kind of just, solve for A. So in this case, A will be R squared mg sine theta over I. So the moment of inertia for a disk, in most cases, is 1/2 mr squared. So the disks that I've chosen at the Discovery Center, they're not exactly this because they have masses attached to these disks. That actually changes the shape and the distribution of the mass for each object. So it's approximately this. We'll say that for a disk where the mass is very close to the center, it'll obviously have inertia that is lower, so we'll say that our inertias for disk 1 is 1/3 mr squared. For disk 2, 1/2 mr squared, and disk 3, 2/3 mr squared. So we can see that we have a disk with lower inertia and then higher inertia. There's also, if you use the parallel axis theorem, an additional plus mr squared here. But like I said earlier, this r is actually from the point of contact. So I'm just going to negate it just because for these disks, that's very, very small. So if we plug this into our formula, I'll just use the 1/3 mr squared, for example. We see that our mass and the radius actually cancel out. So this would give us 3 g sine theta, and that works for each one that you plug in. So you see that the smaller the inertia is, it's actually going to give us a larger acceleration, which in turn kind of predicts which disk is going to reach the bottom of the incline first. So if you watch the videos in just a few minutes, yeah, you'll see each disk go down the incline, and you'll see that the disk with the mass is closest to the center, even though the masses are smaller, actually reaches the bottom of the incline versus the disk with larger masses that are close to the center, and then masses that are far away from the center. So yeah, if you watch these videos, you'll see which one will finish first, and that's essentially a simple way how torque, inertia, and angular acceleration kind of work with each other to show that the mass and radius of an object really don't play into how fast they'll go down the ramp. It's really just the shape and the distribution of the mass about an object and where its center mass is.